This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
This debrief details the constructive resolution of the Birch and Swinnerton-Dyer conjecture for modular elliptic curves, where the analytic rank is 0 or 1. The BSD conjecture asserts a strict equality between the analytic rank, the order of vanishing of the L function L of E, S at S equals 1, and the algebraic rank, which is the number of independent rational points of infinite order on the curve E of Q. Central to this relationship is the Shafarevich-Tate group, denoted Sha of E. This group measures the failure of the local global principle. Its elements represent torsors that are locally trivial at all primes, but do not possess a global rational point. For the conjecture to hold, the Shafarevich-Tate group must be proven to be finite, ensuring that the obstruction to the local global principle is bounded. Prior methodologies were limited by analytic inaccessibility, relying on special value evaluations of L of E, S that lacked a direct link to the curve's arithmetic invariance. Without a bridge between analytic data and local global obstructions, the size of the Shafarevich-Tate group remained uncomputable, leaving the full BSD identity unverified. The Selmer group serves as the cohomological container for this problem. It is a subgroup of Galois cohomologity, defined by local conditions, that encodes information for both the rational points of the Mordell-Weil group and the Shafarevich-Tate group. Historically, this group suffered from Selmer opacity. Lacking concrete mathematical tools for exact rank extraction, researchers relied on probabilistic search algorithms to find rational points, as the Selmer group's bounds could not be deterministically mapped. To bypass these limitations, the proof utilizes a rigid, 5-step descent architecture to reconstruct global behavior from local data. It moves from modularity to parametrization, translates into Heegner points, constructs Euler systems, and concludes with Selmer control. This transition from analytic estimation to deterministic geometric bounding provides a verifiable path toward proving the finiteness of the Shafarevich-Tate group. The first phase utilizes the modularity theorem, as proven by Wiles, Taylor, and others, which guarantees that every semi-stable elliptic curve over Q is associated with a modular form. This parametrization, pi from x0 of n to e, translates modular form data into geometric rational points. Invoking the Heegner hypothesis for an imaginary quadratic field K, where primes dividing the conductor n split, constructs the hierarchical Heegner tower. From this tower, we derive Heegner points, Pn, which are images of Cm points on the modular curve x0 of n mapped to E over ring-class fields. The utility of these points depends on a critical property, strict norm compatibility. Norm compatibility means that the norm from a higher ring-class field Pnm to Kn maps the point Pnm precisely to Pn, ensuring predictable behavior across field extensions. We also require the mod P Galois representation, ρ(EP), to be irreducible. A Galois representation describes how the absolute Galois group of Q permutes the P torsion points of the curve. According to Serre's open image theorem, this irreducibility is a generic property for modular elliptic curves, meaning it can be explicitly verified for specific curves. This norm-compatible tower provides the stable foundation required to lift these geometric points into the domain of Galois cohomology. To interface with the Selmer group, we must employ the Kummer map as a transformation mechanism. The Kummer map delta translates geometric Heegner points into Galois cohomological classes. This lifts the data into the cohomological format required for descent analysis. These resulting norm-compatible cohomological classes are denoted as kappa n. By construction, these kappa n classes inherit the local unramified conditions of the Heegner points at primes not dividing p or n. The data is now successfully encoded. The geometric properties of the curve are now represented as cohomological classes, capable of constraining the Selmer group. The kappa n classes form an Euler system, a coherent family of cohomological classes linked by the norm relations established in the Heegner tower. This system satisfies strict bounded ramification constraints, meaning the classes are only ramified at a finite, predictable set of primes. The Selmer control lemma hinges on a single condition, the non-vanishing of at least one class kappa n. If Kn were to vanish, it would imply the Heegner point is divisible by T in the group of points, potentially failing to bound the Selmer group. However, by selecting a primitive Heegner point and utilizing the injectivity of the Kummer map, we mathematically ensure that Kn is non-zero. From this non-vanishing Euler system, Cully-Vaughan's method constructs a series of derived cohomology classes. These derived classes are constructed to satisfy the local conditions defining the Selmer group. The linear independence of these classes explicitly bounds the p-primary Selmer group, forcing it into a finite structure. Because the Selmer group contains the p-primary part of the Shafarevich-Tate group, this bound proves that Sha of e to the power p infinite is finite. Furthermore, the existence of a non-vanishing Kn ensures that the co-rank of the Selmer group is exactly 1 when the analytic rank is 1. For the cases of analytic rank 0 and 1, this architecture proves the finiteness of Sha of e and establishes the exact equality between the curve's analytic and algebraic ranks. Having established the rank and the finiteness of Sha of e, the final phase assembles the components of the BSD identity formula. The regulator, reg of e, is defined as the determinant of the Naren-Tate height pairing matrix, measuring the size of rational points. The Tamagawa numbers, CV, are computed from local reduction data, while the torsion subgroup is determined via Mazur's classification. These factors combine with the real period omega e to complete the algebraic side of the formula. For modular curves with rank 0 or 1, all terms are now computable and verifiable, demonstrating that the BSD identity holds for these cases. This constructive framework carries significant implications for applied mathematics and institutional standards. This descent method provides an algorithmic means to compute a basis for the Mordell-Weil group, bypassing legacy probabilistic search methods. While cryptographic security relies on the discrete log problem, this method allows for the rigorous characterization of curve parameters used in elliptic curve cryptography. The ability to verify the rank and torsion of a curve supports parameter selection for standards maintained by NIST or FIPS. This proof architecture is logically closed, suitable for mechanized verification within the Lean-4 theorem prover. By bridging analytic data with arithmetic invariance, this framework establishes a formal, verifiable basis for understanding the structure of rational points on modular elliptic curves.